So 11.4 is a chapter on comparison tests. And as a side note, first I want to mention the whole of calculus is about comparing rates. So it's a little bit misleading to just label this chapter comparison tests, because that's actually, this is just one of many, 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 many times in calculus where you need to compare things. Okay, so question, does the following right here, does this guy converge? Okay, the answer is going to be yes, and that's something we already know because it's actually the geometric series where a equals 1, in other words, 1 times anything. So that would be a is 1, and r, see here, if you look, I don't have to put the n there, I can put the n here and it's the same. So now it looks like a times r to the n, and in that case, we know it's geometric, we know it converges. Well, what about if the denominator is a teensy bit bigger? Well, if the denominator is a teensy bit bigger, then that means each fraction, if we pair them up one at a time pairwise, then every term has a smaller buddy, and it's 1 to 1. It's not like every term in the first series has a counterpart, but then there's extras in here missing. It's not like that. It's 1 to 1 pairing. So that means for every single piece in the original term, there's a smaller corresponding piece in the other term. And this goes on for all the terms. So if the first sequence converges to 1, then the second sequence has to converge to something less than 1. How much less? I don't know. But from this pairing alone, there's a sixth that's missing out of the second term. So you cannot argue that they're actually the same. They're not. They're definitely, you can actually measure how far apart they are. They converge to different places. So what about if somebody argues the following? What if they say, okay, so what if somebody says the following, well, 1/2 plus 1/4 plus 1/8 plus 1/16, which was our first is our first series, and then the second one we just slide it over and say, well, you know, you told us that we can throw away any finite number of terms. Well, that's true actually. So what am I going to say now? Well, I'm going to say, I'm going to make a comparison like this, and each successive element, well, these are two completely different series. So the first series adds up to 1 for well, it's okay, let me put it this way. No, they are the same. Okay, this guy went down here. This guy went down here. Sorry. All right. Okay, so then what's happened is I've shifted them, and now I'm saying for each term in the first series, there's actually a bigger term in the second series. So have I now proven that the second series is somehow larger than the first one? Well, actually, that's totally fine, because if we're doing this, we're saying these pieces are a half, this is a half right here, and so it adds up to 1, then that means all these pieces down here have to actually be greater than a half. Well, that's completely valid. That's actually true, and there's nothing inconsistent about that. So you can shift these things around. You're going to get an upper bound and a lower bound, and you can do all sorts of cool things. And all this means is the series is actually bounded between 1/2 and 1. Okay? So this thing is called the comparison test, which in class I called the vanilla comparison test, and I call the other one chocolate. But I'm just going to call this the vanilla, plain old boring comparison test, term by term. So let's use a comparison test to determine that whether or not this converges. Well, you can see that it converges because I'm looking at the notes. This guy converges. Why does it converge? Well, what you should see in your mind's eye is this 5 here just comes along for the ride for free. I mean, it's just there. But you should really kind of see, and here it is again, it doesn't really make any difference to the problem, so it comes along for the ride. But what you should notice is that this polynomial, you know, I want to compare it to something. And so I want to make this guy on the left as simple as possible. I want to make it, you know, like either a geometric or a p-series or harmonic series. I mean, there's got to be something that I'm familiar with. Maybe I'm going to compare it with something that has an integral test that works out nicely. Maybe it's got, like, you know, x times e to the 2x squared or something like that. It's got to have some kind of nice integral. And although it would be like minus 2x squared. But anyway, the point is you want to compare it to a known series. Okay, so this is a known series. Okay, so that's it. So if the denominator of your new guy is bigger, then the whole of the new guy is smaller. And so that's totally fine. And if piece by piece, term by term, it's smaller, then the whole thing is smaller. But only if the original one converged in the first place. So you have to compare this way. You have to be smaller than something that converges to prove that you converge. Or you can be larger than something that diverges and you prove that you diverge. So just make sure you've got that thing going in the right direction. What about the following? 1 over n squared minus n. So you need to get resourceful. And for example, in this case, here's the big hang up here. This is the hang up. It's a minus. If it were 1 over n squared plus n, you would simply say the denominator is consistently larger than, the 1 over n squared variant. And so since the denominator is strictly larger, then the whole thing is strictly smaller, and then you're good to go. But, this is not quite working because we're actually making the denominators smaller, so the whole thing is actually getting bigger. So we just need to be a little bit more careful about how we do this. This doesn't matter for the chocolate comparison test, because you just shove it in and out it comes and it's all fine. And the chocolate comparison test, like the limit comparison test, it does not care whether there's a plus or minus here. It's totally happy either way. But if we want to go ahead and use the vanilla comparison test, and you want to compare these guys, you have to use a little bit of algebra. So this is just algebra. Okay? And so we go ahead and expand n minus 3 squared. Why did I pick that? I don't know, maybe the book did. But it doesn't matter. You can pick n minus 4 and minus 7. Lots of things will work. But you have to shift the guy over, and the whole object of the game is you want to get this to match up, these pieces. I mean, the plus n is not going to, the plus 9 isn't going to cause you trouble. The minus n, you want to make sure that you've got a whole bunch of spare n's so that you can balance this out. Okay, so the n squares are going to cancel out, and then the negative 6n is going to end up on the other side, so you get 5n, 9, and you just, okay, so this is what, 9 over 5 is like just under 2. But since we're dealing with integers, just, as long as n is greater than 2, you're safe. Okay, and that means that for this comparison to work, as long as n is greater than 2, that will work. Now, how does that help us? Well, then what we do is we look at the two series. We look at the 1 minus n squared series, and we look at the 1 over n squared versus the 1 over n squared minus n. We look at these two guys, and we compare term by term. But we can ignore as many pieces as we want off the front of each series. But then once we start pairing them up, then we have to go 1 by 1 comparison. Okay? It has to be like that. Alright, fair enough? Makes sense? I hope so. Alright, we did do this in class and people seem to understand. Okay, so here's the first couple terms. Well, the first couple terms, it's easy to just see. You can stick it in your calculator, and then the second term is definitely smaller. But let's just try it for an arbitrary n, 1 over n squared versus this mess of an expression, and just work out the algebra. Okay, this is just algebra, and you guys know how to do algebra. So you can just prove this. This denominator is going to end up here, and then n squared is going to end up over there. And so if this piece is going to be strictly smaller than 1 over n squared, and so on and so forth, you just work it out. Okay, you guys can do that, and come ask me if you have any questions. Okay, next thing to recall, the diverge. We recall that natural log of n over n diverged, and we could use the integral test to do that. But we could also compare. You can do term by term. Notice that it is larger than 1 over n. So one thing to mention here, again, I've said this before in class, just because a problem can be done one way doesn't mean it's the only way it can be done. There's a lot of problems that can be done multiple ways. And a lot of these things start to sound repetitive because they are. And if you see that they're repetitive, good for you. That's what you're supposed to be seeing. Some people are saying to me, wow, this chapter is so much easier than everything we've done. Well, maybe for you, maybe it's harder for someone else, but it is repetitive, and we do recycle ideas a lot in this chapter. Okay. So limit comparison test, the one I kind of call the chocolate comparison test. It's a little more beefed up. You just stack. You pair up term by term, just like we were doing before, but instead of actually doing the comparison outright, you just make a fraction and take this fraction's limit as n goes to infinity, and both. If you go to a constant, so this thing that mathematicians say, constant which is less than infinity, that less than infinity confuses a lot of students. Just think of it as going to a constant. It just means it doesn't go to infinity. If it goes to a constant, then both series either converge or diverge. And in the case of getting infinity or zero, you just have to think about what you're saying, because a lot of times it means nothing, and sometimes it means something. So for example, if you know the one on top is bigger than the one on the bottom because your limit is going to infinity, but the one on the bottom is diverging, then the one on the top diverges, or vice versa, the opposite. You just take the thing and flip it and you're going to get zero. Anytime you get infinity out of this here and you flip it, you're going to get zero. Okay, so yeah, whenever you use the comparison test, so the one that the book really talks about is this guy. They say if you get a constant, then both series either both diverge or they both converge. But you can use this test in other ways, but you just have to be careful and make sure you don't say the wrong thing. Okay, here's a question. Let's try to determine whether this series here converges or diverges. Well, first of all, you want to just say, what would I want to compare it to? Let's cut to the chase. Let's look at what is dominating the numerator. What's dominating the numerator is this 2n squared. So let's keep that piece. And let's ignore the 5 and just see that this square root of n to the 5th is dominating the denominator. And you just work that out and you end up finding out that that's equal to 2 over square root of n. Well, that's going to diverge because it's very, very similar to 2 over n, right? So 2 over n is the harmonic series. The square roots make the denominators smaller, except for in the case of 1 where it's the same. But for any n larger than 1, then taking the square root of the denominator is going to make the denominator smaller, which is going to make the piece bigger. So we're pretty sure this is going to diverge. But if somebody told us we had to use the limit comparison test, that would be what I would use. Because then I know that when I take my limit, I'm just going to get 1 here, and then I'm good to go. So even though the question may say use the limit comparison test, I'm using something else, right? I'm actually comparing term by term to the harmonic series. But I need to prove that I understand what the limit comparison test is. So once I figure out what my strategy is, I go back and then demonstrate this other technique. That's totally valid. Okay. All right, so what if we want to estimate the first 100 terms of 1 over n cubed plus 1? So the first thing you want to do, and you want to estimate the error, the first thing you want to do is just calculate it, and you're not going to do that by hand. Not even going to do that on your calculator unless you have like a programmable calculator. So you use some software to do that. Okay, so let's say you get this number, or I just pulled it out of the book. What's the error bound? I want you to imagine what's going on here. So you're taking, if you think of each of these terms in the series as being little boxes, you're taking little Riemann sums, but it's the opposite of a Riemann sum. So a Riemann sum is you have an integral that you want to calculate, and you calculate it by drawing little boxes above or below the curve, right? But instead of drawing boxes above or below the curve, you're actually really trying to find the area inside the boxes, and instead you're taking an integral. So you're doing exactly the opposite as a Riemann sum. And so what happens is, if you want to know what the area is, you just, you know, take an integral, but you very carefully place it so that you're either getting little extra pieces by these, you know, see these little triangles that are left over, or else you can slide the curve down here, and then you have extra pieces. And you're either going to under approximate or over approximate. And so in any case, let's say we wanted to get an upper bound. We would calculate this function turns, goes inside the integral and integrate it from 100 to infinity. But that's just an obnoxious integral. I'm not going to calculate that, are you? No. So instead you take this denominator and make it ever so slightly smaller, which means the whole thing gets ever so slightly larger, and that's just good enough for this problem. So that's the way you get around that kind of thing. So you just have to read the question really carefully, and if you're confused during an exam, just come ask me, because if I give you a hint, I'll just give the whole class a hint. Because sometimes it's hard to figure out what the question's really asking, and whether, when it says give an error, sometimes you're not sure if the author wants you to do an upper and a lower error bound, or you just want one. In this case, you want an upper error bound because you're adding up the first 100 terms. So you know for sure that you already have a lower bound on that sum. So what you want is an upper bound on that sum. So, it takes a little bit of practice to figure out what these questions are asking and how to do them.